Bismillah ar-Rahman ar-Rahim. This video is about the simple random walk on the L-dimensional integer lattice. If L is equal to 2, we have 2 dimensions. We start the walk at the origin, the point 0, 0. Then to our current position, we add one of 4 possible vectors. These are 1, 0, minus 1, 0, 0, 1, 0, minus 1, which means that we either move one step to the right if we use this vector, or one step to the left if we use that vector. We can move along the vertical direction. So if we use this vector as our step, then we move upward. If we use this one, then we move downward. We choose one of those vectors with equal probability. So each one of those vectors can be chosen with a probability equal to 1/4. In the general random walk in L dimensions, we have 2L possibilities. So we can choose one of the axes and then either move in the positive direction by one step or in the negative direction by one step. Our random process, our random walk, we will take it to start at the origin. So the initial value is the 0 vector in L dimensions, and then x of n will be the sum of n of those steps, dk. Those steps are independent and identically distributed. Before proceeding, we need to know what is the characteristic function of this random vector dk, which is the step at time instant k. It's a discrete random vector which has 2L possibilities. What is the characteristic function of a random vector? If we have a random vector w, okay, so this is w1, w2, wl. Those are the random variables residing in the random vector w. We have a vector of real value parameters u1, u2 to ul, and the characteristic function of random vector w is expectation e to the I, and then we have the inner product between these two vectors, u transpose w. The inner product is u1 w1 plus u2 w2 all the way to ul wl. So if we want to write down the characteristic function of dk, then it is a summation, and because dk has 2L possibilities, so we have 2L terms. The probability of each possibility is 1/2L, so we can take this as a common factor. Then we have terms in the form of e to the I, and then the inner product between u and each one of those possibilities. So the first term will be the inner product between this vector and that vector, and so it will be u1. The inner product between this vector and this vector, it will be e to the I, and then the inner product will be minus u1, like this, and so forth. These two guys can be combined as 2 cosine u1. These 2 cosine u. This means that we can write down the characteristic function of the step dk as 1/L summation k from 1 to L cosine uk. Again, the steps are IID. In our current position, at each time instant, we add a new step, which can be one of those 2L possibilities, each of them occurring with the same probability 1/2L. Because the steps are independent and identically distributed, we can, in a straightforward way, obtain the characteristic function of our random walk xn. Because those guys are IID, then the characteristic function of x of n is simply the characteristic function of one of those guys raised to the power n. And so this is the characteristic function. What is the goal? What is the objective? The sequence xn is a discrete time Markov chain. Given our current position, the future of the random walk is conditionally independent of its past. The possible states in this discrete time Markov chain are the positions that we are at in the L-dimensional space. Our chain is in fact irreducible, because in principle, every point in the space is accessible or reachable from any other point. This means that the states in this discrete time Markov chain, they all belong to the same class. They are all positive recurrent or null-recurrent or transient. Now, the states in our chain are periodic. If we go to the 2-dimensional case, how can we get back to the origin? To get back to the origin, we need an even number of steps. If we look here, suppose that n is equal to k1 plus k2 all the way to kl. So k1 is the number of times you choose to move along the first axis, either in the positive direction or in the negative direction. K2 is the number of times you use one of these two vectors, the number of times you use the second coordinate, either in the positive direction or in the negative direction, and so forth. Now, let's look at K1, and let's suppose that we want xn to be the O0 vector. Since we are using these two vectors k1 times, then in the first place we have the odd integers 1 and -1. All the other vectors, they contain zeros in the first place. If we want xn to be 0 in the first place, then we need k1 to be even, because the first coordinate will be the sum of the odd integers 1 and -1. How many of them do we have? We have k1 of them. And for the sum of odd integers to be even, we must have an even number of them. So k1 is even. Similarly, if we use any of these two vectors k2 times, these two vectors contain in the second place 1 and -1, odd integers. The other vectors contain zeros. Now, we want xn to be the all zero vector. It must contain 0 in the second place. To get 0 in the second place, then we should have an even k2, so that the sum of the vectors gives 0 in the second place. If k2 is odd, then we have in the second place an odd number of odd integers that are added together, and the result will be odd. So it cannot be 0. Following a similar logic, every k here must be even, and n is even. X of n is the all zero vector in the L-dimensional space if and only if n is an even integer. So the probability to go from the all zero vector to the all zero vector, this probability to be positive, you need an even number of steps, 2m. To know the class of state 0, the state at which we are at the origin, then we need to investigate the limit of this probability as m tends to infinity. And we need to investigate the sum of those probabilities over m. So we need to investigate the limit and also the sum. Now, the possibilities are, if the limit is positive, then we have a positive recurrent state. And because the chain is irreducible, then all states will be positive recurrent. If the limit is 0, then we have either null-recurrent states or transient states. In that case, we go to the sum. If the limit is equal to 0 and the sum is plus infinity, then we have null-recurrent states. Note that this summation here gives over all time the average number of visits to the origin, starting from the origin. So if this summation is plus infinity, it means that the origin is visited infinitely often, and it will be a null-recurrent state if the limit is equal to 0. Now, if this summation is a finite number, then we have a transient state, because it means that over all time, the average number of visits to the origin from the origin is a finite number. Our investigation now will focus on computing the limit and the summation so that we are able to classify the origin. Once we do this, and because the chain is irreducible, then we know the class of each state. We are interested in this probability, but previously we have obtained the characteristic function. They are related through this integral. This integral is the inversion formula that allows us to compute or obtain the probability given the characteristic function. If we use this integral here, we obtain the probability that x of n is the all zero vector, given that we start at the all zero vector, the origin of the L-dimensional space. Now, how can we obtain the limit? We replace n by 2m, because now the period of the all zero vector is 2, because the all zero vector can only be visited at even instance of time if we start at the origin. And also we have a rule that if the discrete time Markov chain is irreducible, then every state will be periodic, having a period of 2. So we replace n by 2m in our formula, and now let's try to take the limit. Recall that this limit will decide for us whether we are talking about a positive recurrent state. This is the case if the limit is strictly positive. For periodic states, the limit should be a positive number, specifically the period over the mean recurrence time of the state, which is a finite number for positive recurrent states. If we get a limit that is 0, then our state is either null-recurrent or transient, and then we need to investigate the sum to decide which is which. So let's start by taking the limit. Now we have the limit of an integral. The integration that we have here is an L-dimensional integral. It is an integral from -pi to pi, -pi to pi, L times, and our integration variables are the u's, the real valued parameters of the characteristic function, du1, du2 to dul. We have a limit and we have integral. So how can we take the limit? Well, let's investigate the integrand. Let's try to upper bound the function 1 over L summation k from 1 to L cosine uk. The magnitude of this sum by the triangle inequality is upper bounded by 1 over L summation k from 1 to L, the magnitude of cosine uk. And the magnitude of cosine is less than or equal to 1. So this is less than or equal to 1 over L summation k from 1 to L of 1. And so this is 1 over L times L. And so this is 1. 1 to the power 2m is 1. So the integrand can be upper bounded by 1, can be upper bounded, and the upper bound is independent of the variable with respect to which we are taking the limit, which is m. Moreover, if we replace the integrand by 1 and we try to integrate, we will get a finite result. The finite result will be, if you put 1 here, then each integral will give you 2 pi, and the overall integral of the upper bound will be 2 pi all to the power L, which is a finite number. So because we can upper bound the integrand by an upper bound that does not depend on m, and because the upper bound is integrable, then by the dominated convergence theorem, we can take the limit inside. Now we take the limit, and we have a quantity here that is less than or equal to 1, raised to the power 2m. But when is this quantity equal to 1? It is equal to 1 if all the u's are equal to 0, so that the cosines are equal to 1. Or the u's are a mixture between pi's and minus pi's. In both cases, cosine pi or cosine minus pi is minus 1. If all the cosines are equal to minus 1, this summation will be equal to minus L, and the magnitude will be equal to 1. These are the only cases in which this bracket is equal to 1. Otherwise, this bracket is strictly less than 1. So this bracket is 1 only on a set of measure 0 in the L-dimensional space. Otherwise, this bracket is less than 1. And because we have something less than 1 raised to the power 2m, when we take the limit as m goes to infinity, the limit is 0, and the integral of 0 is 0. The limit is 0. And because the limit is 0, we now exclude the possibility that our state is positive recurrent. Our state is either null-recurrent or transient. Let's investigate the sum. There is no problem now if we use n again. We know that if n is even, this probability is positive. If n is odd, this probability is. We will make use of the generating function. So suppose that there is z in the interval between 0 to 1, 1 excluded, so z is strictly less than 1. The generating function is the sum of the probabilities times z to the power n. Now we have the probabilities represented in terms of the characteristic function. So recall from the previous page that the probability is 1 over 2 pi to the power L, and then we have an L-dimensional integral. Every integral is from minus pi to pi, and we are integrating with respect to the u's. And what we are integrating is this quantity, which is 1 over L summation k from 1 to L cosine uk, or raised to the power n. What we do now is multiply by z to the power n. So when we multiply by z to the power n, z can come here. Okay, this is this z, and then we do a summation. The summation is from 0 to infinity. Can we interchange the order of the infinite sum and the integral? Let's replace this quantity by its magnitude. In fact, we can upper bound the magnitude by the magnitude of z. Recall from the previous page that the upper bound on this summation with the factor 1 over L, this is less than 1. And so this magnitude is less than or equal to the magnitude of z. And z is chosen to be strictly less than 1 in magnitude. Replacing this by magnitude of z to the power n. Now, can we do the summation and integration? If we apply the infinite sum and integral to this magnitude of z, which is an upper bound on what we have here, then the integral will give us 2 pi to the power L, and the sum will give us 1 over 1 minus the magnitude of z. We have a convergent geometric series, and this is a finite number. So by Fubini, we are allowed to interchange the order of integration and summation. What we will do is that we will take the summation inside. The probability generating function is 1 over 2 pi to the power L, and then the L-dimensional integral. Now we have summation n from 0 to infinity, and we have this quantity here raised to the power n. From above, we know that this is a geometric series with a ratio that is less than unity in magnitude. And so this is a convergent geometric series again. We can sum it and get a finite result. The generating function is our way to obtain the sum, this summation here, and this summation, if infinity, the states are not recurrent, if finite, the states are transient. In order to obtain the sum, we apply Abel's limit theorem, which tells us that this summation can be obtained via taking the limit of b00 of z as z approaches 1 from the left. So we need to take the limit of this integral. For this purpose, we split the integral into 2 parts. In one part, we have the sum of the cosines is non-negative, and in this other part, the sum of the cosines is negative. Now, in this integral, the sum of the cosines is negative, and so the integrand is in the form of 1 over 1 plus something that is non-negative. This means that the integrand is less than or equal to 1. That's an upper bound that is independent of z. And if we replace the integrand by the upper bound 1 and do the integration, we get a finite result. the integration can be upper bounded by the full integral from minus pi to pi for each u. And in that case, we have an upper bound of 2 pi to the power L, which is a finite number. So for this integral here, again, the integrand can be upper bounded by 1, and 1 is integrable. And so by the dominated convergence theorem, if we want to take the limit as z tends to 1, we can move the limit inside, and we can take the limit. This is for the second integral here. And if we take the limit as z tends to 1, this z will just become 1. Okay, so this will be 1. What about the first integral? In the first integral, this summation is positive. So we have 1 over 1 minus z times a positive number. Now we cannot upper bound this magnitude by unity like what we did here, but what we can see is that this becomes a monotonic function in z. If you have a function 1 over 1 minus z times a positive number that is less than 1, then this function is monotonically increasing in z, and the integrand is a non-negative value. So we can apply now the monotone convergence theorem when we take the limit. By the monotone convergence theorem, we can take the limit inside, and this z will be 1. And then we can recombine the two integrals again, and this is what we have. This is the summation n, which is a non-negative integer, of b00 of n. And if we look at this integral, it's not clear whether this integral is plus infinity or a finite number. So further investigation is needed. If we stare at this integral, what can go wrong? This quantity. If the u's are equal to 0, cosines are 1s, the sum is L, L over L is 1, we have 0 in the denominator. We are integrating over the region from minus pi to pi for every u, u1, u2, and so on. We have this L-dimensional box. But based on this observation, it seems that the way to go is to split the integral into two integrals. In one of them, we will focus on the origin. So we will restrict the domain of integration to an open ball of radius epsilon, some positive number centered about the origin, and then the rest of the domain of integration. This integral here is finite. We can show this by using the inequality that cosine theta is less than or equal to 1 minus 1/5 of theta squared, theta between minus pi and pi. And this can be verified using standard calculus techniques. So we can take g of theta as 1 minus 1/5 of theta squared minus cosine theta. Then we can obtain the minimum of this function. So the minimum of this function using calculus will be when theta is equal to 0, which means that g of theta for theta between minus pi and pi is lower bounded by g of 0. And g of 0 is equal to 1 minus 0 minus cosine 0, which is 1. So the minimum is 0. What we can do now is to take this inequality and apply it to cosine uk. Cosine uk is less than or equal to 1 minus 1/5 of uk squared. We can write down this inequality for u1, u2, all the way to ul. And then we can sum the inequalities, and then we can divide by L. So the left-hand side becomes 1 over L summation k from 1 to L cosine uk. This one, when it is summed L times, it gives L. L over L is 1. And then when we do this summation here, we will get minus 1/5 times 1 over L, and then summation uk squared, k from 1 to L. And this is exactly the L to norm squared of vector u. Now we can move this to this side, and we can move this to the other side. So 1 minus 1 over L summation k from 1 to L cosine uk is greater than or equal to 1 over 5L times the L to norm squared of vector u. Now taking the reciprocal of both sides and reversing the direction of the inequality, now we have an upper bound on the integrand that we have here. 1 over 1 minus 1 over L summation k from 1 to L cosine uk is less than or equal to, then we have the reciprocal of this side, which is 5L divided by the L to norm squared of vector u. This integration here, note again that it is over the L dimensional box, where each u is from minus pi to pi, excluding the ball about the origin with radius epsilon. This integral is upper bounded by 5L. Then we are integrating the reciprocal of the L to norm squared of vector u. Now, what is this integral? We do not really need to evaluate it exactly. We know that this integration avoids the ball with radius epsilon, which means that over the domain of integration, the L to norm squared of any u vector will be greater than or equal to epsilon squared. Thus, the reciprocal of the L to norm squared is less than or equal to 1 over epsilon squared. And then the integration itself can be upper bounded by 2 pi to the power L. Everything here is finite. Now our focus will be this integration here, which includes the origin. The fate of our problem, whether the states are null-recurrent or transient, will depend on this specific integral. Because if this integral is finite, this summation is finite and the states are transient. If this integral is infinite, the summation is infinite and the states are null-recurrent. Now we need again to use inequalities. Let's see what inequalities we should employ to manage this integration here. Let's do the second order Taylor polynomial of cosine theta about 0. So cosine theta, if we differentiate with respect to theta, we get minus sine theta. And then if we differentiate again, we get minus cosine theta. So this means that cosine theta is equal to cosine 0, which is 1. The linear term theta will be multiplied by the first derivative of cosine theta evaluated at theta equals 0. So here we will have 0. And then we will have the quadratic term, so theta squared and 1 over factorial of 2, which is 2. And then this will be multiplied by cosine zeta. And zeta is a number between 0 and theta. So the second order Taylor polynomial for the cosine about 0 is cosine theta is equal to 1 minus theta squared over 2 cosine zeta. Cosine zeta is less than or equal to 1 minus theta squared over 2 is non-positive. So if we multiply both sides of this inequality by minus theta squared over 2, we get minus theta squared over 2 cosine zeta greater than or equal to minus theta squared over 2. We add 1 to both sides. And so we have 1 minus theta squared over 2 cosine zeta is greater than or equal to 1 minus theta squared over 2. Let's now restrict ourselves to theta in the range from minus pi over 4 to pi over 4. In this range, if theta is in this range and zeta is between 0 and theta, then cosine zeta is greater than or equal to 1 over square root 2. Theta is between minus pi over 4 to pi over 4. Zeta is in the same range, and cosine zeta is greater than or equal to 1 over square root 2, which is cosine pi over 4. Now again, multiply by the non-positive quantity minus theta squared over 2. So minus theta squared over 2 cosine zeta is less than or equal to minus theta squared over 2 times 1 over square root 2. Add 1 to both sides. And now we have that 1 minus theta squared over 2 cosine zeta is less than or equal to 1 minus theta squared over 2 times 1 over square root 2. So now we have a sandwich. We have cosine theta, which is 1 minus theta squared over 2 cosine zeta. This is lower bounded by 1 minus theta squared over 2. Also, it is upper bounded by 1 minus theta squared over 2 times 1 over square root 2. So now for theta, use UK, where k is 1, 2, all the way to L. So we have L inequalities. Cosine UK is between 1 minus 1 half UK squared and 1 minus 1 half UK squared times 1 over square root 2. We then add k from 1 to L and divide by L. So this will be the term that appears in our integral. When we add this and divide by L, we get 1 minus 1 over 2L, the L to norm squared of L. Here we get the same thing, but we have an extra 1 over square root 2. We can multiply by minus 1 and then add 1. So we'll get this inequality. We then take the reciprocal of all sides, and then we have this inequality here. That 1 over 1 minus 1 over L, summation k from 1 to L cosine UK, is between 2L over the L to norm squared of U, and the upper bound is 2 times the square root of 2L over the L to norm squared of U. We can integrate all sides, and now the integral, this integral here, will be bounded by an integral that is proportional to the integral of 1 over the L to norm squared of vector U. Now, if this integral is finite, then this upper bound will be finite when we integrate, and our integral of interest will be finite. If this integral here is infinite, then this lower bound, when we integrate, will be infinite, and the integral of interest will be infinite. So this means that both integrals converge or diverge together. And note that the sum of n 0L by 1, 0L by 1, these two guys also converge or diverge together. The classification of states now is the matter of determining whether this integral is finite or infinite. This restriction here on the values of the u's is not a problem at all. This integral, the domain, is this ball with radius epsilon, the L to norm square of vector u. So u1 squared plus u2 squared all the way to ul squared is upper bounded by epsilon squared. And we can choose epsilon to be as small as we wish. So the u's are really small here in this domain of integration. We do this integration by using spherical coordinates, exploiting the fact that the integrand depends only on the norm, the L to norm of vector u. So let R be the L to norm of u, and our integral will be from 0 to epsilon, and then 1 over the L to norm squared will be 1 over R squared. And then we will have here some positive constant r to the L minus 1 dr. This is a very doable integration. The exact value of KL, this constant, which will depend on the dimension, does not really matter. It is just some positive constant. Now, we will have integral from 0 to epsilon, and then we have r to the L minus 1 over r squared dr. If L is equal to 1, if we have this walk, this simple random walk in one dimension, which means that we just move one step to the right or one step to the left. In this case, L is equal to 1. The numerator is 1, and we are integrating 1 over r squared. The integral of 1 over r squared is minus 1 over r. So it is 1 over r, and then we use the lower bound 0. Oh, this will give plus infinity. This integral here will give us infinity. Recall that these two guys converge or diverge together. If the integral is plus infinity, then this summation is plus infinity. In this case, the state of the origin, the all zero vector in L dimensions, will be null recurrent. And because the Markov chain is irreducible, then every state will be null recurrent. Now let's try to work this integral in 2 dimensions. If L is equal to 2, now we have r in the numerator and r squared in the denominator. Now we have the integral of the inverse of r. This will give us a logarithm, and again, we will get infinity when we use 0. In this case of 2 dimensions, also the states will be null recurrent. Now, suppose that we are in 3 dimensions or more. So in the numerator, we have r squared or r cubed and so forth. You will find in those cases that the integral is finite. For example, if L is equal to 3, the integral is just epsilon. If L is strictly greater than 3, then the integral will be epsilon to the power L minus 2 over L minus 2, which is finite. In this case, the summation is finite. This summation gives the average number of visits to the origin, given that we start in the origin. Now, when the number of dimensions is 3 or more, then the average number of visits over time is finite, indicating that our states are transient. The conclusion is that if we do a simple random walk on the L-dimensional integer lattice, the states of this discrete time Markov chain are transient if L is greater than or equal to 3. If L is 1 or 2, then the states are null recurrent.